So let's introduce the visible spectrum briefly. And what we know so far is that light has evidence for it being a wave in nature. So we have plenty of evidence for that. And there is two important fundamental characteristics of light. That's the intensity, which is related to the square of the amplitude, and also its color. So we haven't talked about color yet, but that is related to the wavelength. So the wavelength of light determines the color. Now, visible light is just that sliver in the electromagnetic spectrum that our eyes respond to. The photons that correspond to a certain wavelength. I'm interchanging photons and waves here. Particles and waves, basically. And it's the wavelengths that fall between 400 nanometers to 750 nanometers. And I think our doggies are about ready to get fed, so they're making a racket. All right, so that is known as the visible spectrum. The visible spectrum. So here is a graphic of the spectrum of light. Notice the frequency going up this way. Notice it's a logarithmic scale, exponential in this case. All right, so you're from 10 to the 0 to 10 to the 24. 24 orders of magnitude of frequency, and thus wavelength, which is increasing wavelength as the frequency goes down, because the speed of light is constant. So there are an incomprehensible number of different functional wavelengths in nature that we have in part access to, but our eyes only have access to this little sliver from 400 to 700, 750, depending. And if you can make this a linear scale and stretch it across the entire Earth, the amount of that bandwidth, basically the amount of those frequencies or wavelengths that correspond to visible light, would just be a sliver still if this was a linear scale. So essentially the visible spectrum is almost none of the entire electromagnetic spectrum. But of course it's important to us humans because it's the part that we directly have access to. And incidentally, the sun itself shines most brightly right in here, kind of the greenish region of the visible spectrum. Isn't that something? So, of course, we evolved in the context of the Earth-Sun system, and so that alone, even though we don't know the details, kind of makes sense that we would end up with greatest sensitivity in the middle. Our visible sensitivity would be most sensitized right where the sun is at its peak intensity. All right, anyway, the sun actually produces ultraviolet and infrared as well, which are shorter wavelength and a higher wavelength light. All right, so anyway, just to point out that the visible spectrum is really, really a small part, but that's the part we're most interested in right now. And it turns out that the index of refraction, which we've discussed, of a particular material is not just a constant. It has a dependence on the wavelength itself. And we saw that briefly with water waves. When we have a slower medium, if the medium changes a little bit, that's one thing. You have refraction. But the amount of refraction has to do with the actual frequency of the waves also. So for visible light, where it's perhaps more important, we actually have a relationship between the index of refraction and the wavelength. So here's the visible spectrum, and it looks kind of like this. So say for glass, at red, we would have 1.5 index of refraction. And that index of refraction goes up as we go through the various colors, from red to yellow, orange, yellow, green, blue, violet. So the index of refraction actually increases a little bit. So it's because of this that white light, which has all the colors, gets separated into all the colors that make it up, because of this differing amounts of refraction. So violet is refracted the most, red is refracted the least, and that effect is called dispersion, which you've heard that before. And so a quick peek here, visual at what this looks like. So here's white light coming in to this prism, and that starts and refracts all the wavelengths. But the red, notice the red is bent the least, and the violet is bent the most, and all the other colors in between. So that's exactly how and why the a prism will give a spectrum of colors. We'll show all the colors. Each color corresponds to a different wavelength. Wavelength decreasing in this direction from red to violet, and therefore the refraction increasing in that direction. So that's dispersion, and that will be an important concept in producing rainbows, which will be our next little lesson.